In today's video, we're going to take a closer look at the electrolysis of aqueous solutions, that is, ionic compounds that have been dissolved in water. In our last few videos, we saw that electrolysis is a technique used to split chemical compounds into their individual elements by passing an electric current through a liquid or solution known as an electrolyte. For electrolysis to happen, the ions inside the electrolyte must be free to move because it's this movement that allows the electrical current to carry out chemical changes. Now, when we deal with insoluble compounds, such as most metal oxides, we have to melt them to make them molten liquids. Only then can the ions move freely. But if our compound is soluble, such as copper sulfate or sodium chloride, we don't need to melt anything. We simply dissolve it in water, and that solution becomes our aqueous electrolyte. So, in today's lesson, we'll focus on understanding how electrolysis works in these aqueous solutions and how to predict what happens at each electrode. Let's start with the basic setup for an electrolysis experiment. We'll need a beaker containing our electrolyte solution, two electrodes, the positive electrode called the anode and the negative electrode called the cathode, connected by wires to a power source, such as a battery. When the current is switched on, electrons flow through the circuit, and the ions in the solution begin to move towards their respective electrodes, depending on their charges. However, there's a small challenge when dealing with aqueous solutions. In addition to the ions from the compound itself, water also ionizes slightly, producing hydrogen ions, H, and hydroxide ions, OH. This means that in any aqueous electrolyte, there are 4 types of ions present, 2 from the solute and 2 from the water. As a result, we have to determine which ions will actually be discharged at each electrode. To figure that out, there are a couple of simple rules you need to remember. First, let's look at the cathode, which is negative. The cathode attracts positive ions. These include the metal ions from the compound and the hydrogen ions from the water. However, not both will be discharged. Only one type of positive ion actually gains electrons. The rule here is that the ion of the less reactive element will be discharged. If you check the reactivity series, you'll see that hydrogen is less reactive than metals like sodium, magnesium, zinc, or iron. So if your solution contains any of those highly reactive metals, it's the hydrogen ions that will be discharged at the cathode instead, forming hydrogen gas. But if the solution contains a less reactive metal such as copper, then the metal ions, in this case copper ions, will be the ones discharged to form solid metal. Now, let's move to the anode, which is positive. The anode attracts negative ions, typically the nonmetal ions from the compound, such as chloride, bromide, nitrate, or sulfate, as well as the hydroxide ions from the water. The rule for the anode is a bit easier to remember. If there is a halide ion present, that's a fluoride, chloride, bromide, or iodide, then the halide ion will be discharged. But if no halide ions are present, then it's always the hydroxide ions that are discharged instead, producing oxygen gas. Let's apply these rules in practice with a few examples. Example 1. Electrolysis of copper, 2. Sulfate solution. If our electrolyte is an aqueous solution of copper sulfate, the ions present will be from copper sulfate, Cu superscript 2 and SO4 superscript 2. From water, HNOH. At the cathode, the positive ions that could be discharged are Cu superscript 2 and H. Checking the reactivity series, copper is less reactive than hydrogen, so copper ions will be discharged. Each copper ion gains 2 electrons to form pure solid copper, which coats the cathode with a thin, reddish-brown layer of metal. At the anode, we have the negative ions, SO4 superscript 2 and OH. According to our rule, because no halide ion is present, it's the hydroxide ions that will be discharged. Each hydroxide ion loses electrons to form oxygen gas and water. The half equation for this reaction is 4OH, 2H2O plus O2 plus 4E. So overall, during the electrolysis of copper sulfate solution, copper metal forms at the cathode and oxygen gas is released at the anode. Example 2. Electrolysis of sodium chloride solution. Now, let's look at aqueous sodium chloride, commonly known as brine. The ions in this solution are from sodium chloride, Na and Cl, from water, HNOH. At the cathode, we compare H and Na ions. Since hydrogen is less reactive than sodium, hydrogen ions are discharged. Each hydrogen ion gains one electron to form hydrogen gas, H2, which bubbles off at the cathode. At the anode, the two negative ions are Cl and OH. According to our rule, halide ions are always discharged in preference to hydroxide ions, so chloride ions lose electrons to form chlorine gas, Cl2. You'll usually notice small bubbles forming around the anode. That's the chlorine gas being released. So, in the electrolysis of aqueous sodium chloride, hydrogen gas is produced at the cathode and chlorine gas is produced at the anode, while sodium hydroxide remains dissolved in the solution. This process is actually used industrially in what's called the chlor-alkali process, which produces hydrogen, chlorine, and sodium hydroxide, three very important chemicals for manufacturing. To summarize everything, in the electrolysis of aqueous solutions, water contributes its own ions, H and OH, meaning that predicting the products requires understanding reactivity and discharge rules. At the cathode, the less reactive positive ion is discharged. At the anode, a halide ion is discharged if present. Otherwise, hydroxide ions are discharged. These simple rules allow you to predict what elements will form at each electrode in any aqueous electrolysis experiment. In the next lesson, we'll take a deeper look at the equations and energy changes involved in electrolysis, so you can understand not just what happens, but why it happens the way it does.